So this is the session on DNS and security. It's a fairly packed agenda. We have an invited talk on Dragon Blood, discussing some problems with WPA3 that will hopefully be of very much interest to the security and cryptography people in the room. And we have several talks on DNS, both with the lens on privacy, performance, and security. So without further ado, I'd like to introduce Matthew Venhoff. He is a postdoc at NYU. Let's give him a round of applause as he gets started.
Good morning, everyone. So thank you for the introduction. So I'm going to be talking about WPA3 and specifically about the Dragonfly handshake that is used now in this protocol. And this Dragonfly handshake, it's also used in EPWD. And this research was done in collaboration with Eyal Ronen. So to give a very quick background, Dragonfly is a password authenticated key exchange, which means it provides mutual authentication. It negotiates a session key, which you can, after the handshake, use to encrypt actual communications. And more importantly, it is a handshake that provides forward secrecy and it defends against dictionary attacks. Now, in the case of Dragonfly, there is no protection against a server compromise. So concretely, let's say in the case of WPA3, if an attacker would somehow get access to the access point, the attacker would obtain enough information to easily authenticate as a client. While recently there are also some PIGs that have been introduced that also protect against a server compromise by introducing some kind of salt. So what we did is we analyzed the security of Dragonfly, and to explain the things that we found, I'm going to quickly introduce the most important concepts of this handshake. And to do this, I'm going to assume that we have a client here that wants to connect to the access point. And the first thing that has to be done with the Dragonfly handshake is that we have a shared password, which can just be an ordinary ASCII string. And this is converted to either an elliptic curve point or in general into a so-called group element that we call P. And this P can then be used in the cryptographic calculations. So the handshake consists of two main phases. I'm not going to go into detail. Basically, we first have the commit phase where the actual session key is being negotiated. And then there is, at least in the case of Wi-Fi, a confirm phase that confirms that both parties indeed used the same password and that they negotiated the same session key. And the important question here is, how is this password converted to a group element? And I'm going to start with the simple case here, where we are using so-called mod P groups. So these are not yet elliptic curves, because the Dragonfly handshake also supports mod P groups. And here the algorithm is a bit simpler to explain, and it also nicely illustrates the flaws of this method. So an intuitive and a little bit naive way to convert the password into a group element is to simply take the hash of the password. In the case of Wi-Fi, we also combine it with the MAC addresses of the client on the server. So in other words, we include the identities of the peers. We then take the output of that hash value. We perform some calculations to get a p-value that is an element of the cryptographic group we are using. And then we do a quick sanity check to make sure that we have basically a valid and secure element. And in practice, this check always succeeds. So this would be the intuitive way to convert the password into a group element. But there is one thing that is missing here. The problem is that our hash output here, our value, it can be bigger than the prime of the group that is being used. And in this case, the calculations that we did here wouldn't be valid. So how do we avoid this? Well, the way that it was decided to do this for Dragonfly was to simply include an if test here. If the value is bigger than the prime, then, well, we try again. In other words, we include a counter here. We always increment it by 1 until we get a hash output that is bigger than the prime, and then we can continue. Now, of course, this leaks time. There's a side channel here. And in fact, in mailing lists of the IETF and the CFRG, people warned about this. They said, this doesn't look good. You should do something else. But unfortunately, for the case with the mod P groups, this recommendation was never included in the specification. And this, of course, leads to a trivial, well, a rather easy timing attack. So one thing that makes this timing attack a bit more interesting here is that we can pretend to be client A. We can then measure how many iterations it took to find the password. And because the identities of the clients are included here, in the case of Wi-Fi, we can then spoof another MAC address. We can try to connect with the access point, and then we can see how many iterations it then took using another MAC address. Then we can spoof another client, and we can spoof a lot of clients. And each time we can do a timing attack to measure how many iterations this algorithm took to find the group element. So we tried this attack by setting up a Wi-Fi access point, so a WPA3 access point on a bit of an older Raspberry Pi. And the reason we picked a Raspberry Pi here is because its CPU is actually similar to the one of a professional Wi-Fi access point. And when we then did this timing measurements, we found out that indeed these differences can be easily measured simply over Wi-Fi. So you can see the example here where we have the blue full line. It corresponds to the timing response if the algorithm only takes 1 iteration. Then we have the case where it takes 2 iterations, 3 iterations, and so on. And in practice, we found that against our target, if we make 75 timing measurements, then we can accurately tell how many iterations it did. So this is the case against WPA3. And if we would perform a similar attack against the EPWD protocol, against the so-called IWD client, which is a Wi-Fi client in Linux, this implementation is a bit slower. And here, if you make 30 connection attempts, you can accurately determine how many loops were needed. So we now know that there's a timing leak. We can derive the number of iterations that were being used. But now the question is, does this really leak important information? In other words, can we abuse this to, for example, perform a dictionary attack? And the answer is yes, we can. Let me take the following example. We are, say again, attacking a WPA3 access point. We spoofed a client MAC address of A, and we measured that in this case the access point took 2 iterations to derive this group element. Well, what we can then do is we can guess some passwords. In our example here, we're trying 3 different passwords, and we can then simulate this method that converts the password to a group element. We can simulate it offline on our own PC. And we can notice here that, for example, for password 1, it only uses 1 iteration, which doesn't correspond with our measurements, so we can exclude the password based on that. On the other 2 passwords, they're still possible. So then we can spoof another MAC address B. We can again measure how many iterations it takes in the real world. We can compare this to our simulated results, and we can continue this way and exclude passwords that don't match our observation. And we can continue doing this until we uniquely determined the password that is being used. So in this example, it's password 3 that matches our observations. And In general, if, for example, you want to test a dictionary of 10 to the power 7 passwords, which is roughly the same size of the RockU database password leak, then we need to do this attack for about 17 MAC addresses. And in practice, we found that this is quite feasible in just a few hours of time. And the conclusion here is that the number of iterations that are executed, they essentially form a signature of the password that is being used, and we can use that to then do an offline brute force attack. So I now covered the case when we used mod P groups, but Dragonfly also supports elliptic curves. So the question is, are they affected as well? And luckily, if we at least use NIST curves, then Dragonfly is not affected, because in that case, they essentially listened to the warnings of the IETF and the CRFRG mailing list people, and they included some defenses against it. Unfortunately, Dragonfly also supports brain pool curves, and interestingly, initially, we didn't look at these brain pool curves because Dragonfly supports of a lot of parameters, so it's hard to analyze every possible scenario. But the reason we did look at brain pool curves is because after our initial disclosure to the Wi-Fi Alliance, they privately created some recommendations on how to avoid our attacks. And in those recommendations, they said, okay, you can use brain pool curves. They are safe to use. There are no timing attacks against them. Unfortunately, when we checked that, there's bad news. Actually, if you do use brain pool curves, you are vulnerable. So here we also fall back to the typical security advice. Don't write recommendations on security advice privately, but we should all know that already. So I want to briefly give some insight into why these brain pool curves also have timing leaks. So to do this, I'm going to do the same thing like I did with the mod P group. I'm going to briefly explain how the algorithm works to convert a password into an elliptic curve point, and I'm then going to explain where this timing information is leaked. So if you would want to hash a password to an elliptic curve point, a naive idea would again be to just take the password. In this case, we again combine it with the MAC addresses of the client and the access point. We take the hash output as the X value, and then we just find the corresponding Y value and use that as the elliptic curve point. But you may probably now already have one remark about this, namely, there's not always a solution for Y. So what can we do? Well, the first thing we can do is we can calculate this value here, which is basically Y squared, and we can see if it is a so-called quadratic residue. And if this value is a quadratic residue, then we know that a solution for Y exists. And to handle the case if there is no solution, we again just perform a loop. In other words, we include the counter in our values that are being hashed, and we continue executing loops until we found a solution where we can, where the square root exists. Now, there's one problem with this, and this is that now different passwords again have a different execution time. Now, luckily, in the case of elliptic curves, they listened to the warnings and they included a suggested defense of always executing k iterations, no matter when the password was found. And in practice here, they generally use a value of k equal to 40. So no matter when the password is found, you're always executing 40 iterations. And this prevents at least the timing attacks against NIST curves. There is one other extra defense that they included here, which is that once the password has been found, they execute these extra iterations based on a random password. Now, this is just defense in depth in case that there is something wrong with the code. That's the best way to explain that for now. Now, what is the problem here? The problem is quite similar to the mod P case. So maybe some of you can already figure it out. The problem is, again here, this hash value that we get here as output can be bigger than the prime that is being used in this cryptographic group. And what was the solution here? Well, they again just say that if the value is bigger than the prime, just go to the next loop. And you can see the problem here. The problem is that if this value is indeed bigger than the prime, then we don't do these quadratic residue tests, and we again get different execution times. Now, the interesting thing here, if we use NIST curves, the probability of this condition being true is very low. But with brainpool curves, this has a probability of, say, between 20 to close to 50%, depending on the specific curve you're using. And in that case, the quadratic test may be skipped. So again, we're in trouble. Now, the timing attack against this case is a bit less straightforward, because we do still have these extra iterations that are being executed. And on top of that, these extra iterations that are executed after the password element has been found, they are based on a random password. So to quickly illustrate the impact of this in practice, let's say I perform some executions using the same MAC address. Then in this case here, green illustrates that I executed the quadratic residue test in a loop. The small bar here illustrates that the hash output was bigger than the prime, so there's no quadratic test. And say that after 4 iterations, we found the password. So at that point, extra iterations are executed based on a random password, so we get some amount of extra time that the algorithm takes. If you now execute the algorithm again, we always have that the first iterations, they are identical because they're based on the real password. But these extra iterations, they use a random password. So each time we also get a random amount of extra time that is being added to the execution. But even with this, it leaks sensitive information, because now the variance of the execution time depends on when the password was found. For example, if the password is immediately found after the first iteration, you get a lot of variance. But if the password was found, say, after 20 iterations, you get a low amount of variance. On top of that, the average execution time also still leaks information, because that depends on the number of iterations needed to find the password and how many of those iterations had a hash output bigger than the prime, so there was no quadratic residue test. So again, we have the same case here, that this forms a signature of the password, and we can use that in an offline dictionary attack. And if we perform this test again against a Raspberry Pi, we again notice that this timing information can be measured over Wi-Fi. In the case of Brainpool, we need to make more measurements per MAC address because the timing differences are smaller, but it's still feasible to do this in practice in a few hours. So another possibility here, and I'm going to cover this very briefly, instead of doing timing attacks, we can also do cache attacks. Basically, we have the same algorithm as before, and we can basically use flush plus reload to detect when the password was found. We can do the same thing with Brainpool. We can use flush and reload to detect when the hash output was bigger than the prime. Now, I'm not going to discuss much more because I don't have time for this. We actually found a lot more interesting things. We also found some implementation-specific vulnerabilities in EAP PWD. And the one I want to highlight is that if you use bad randomness in Dragonfly, then you can recover the plain text password. So that's one thing to take into account. Maybe if you design a handshake like this, I think it's good to also discuss what would be the impact if there is a flawed source of randomness. We also found attacks specific to Wi-Fi, but I'm not going to mention them here. And the interesting thing here is that finally the Wi-Fi standard is now being updated to use a constant time algorithm to find the password element, and maybe this will be included in WPA3, I'm not sure, but at least on the Wi-Fi, on the 802.11 group, they are working on it. So with that, I'd like to conclude my talk. Thank you for your attention.
So we have time for probably one quick question, and then we have to move on to the next presenter. If that person can come up, get ready. That would be great.
Okay. The first two attacks you showed.
Speak a little closer.
I'm sorry. The first two attacks you showed looks like they could be relatively simply worked around by redesigning exactly how the code works, by iterating as many times and always performing the QR test, even if P is greater than if the point is greater than P. Are your other issues that you haven't addressed? You haven't talked about? Are they also can be worked around?
So there are workarounds, but they are not a deal in practice, because we saw in practice that, I mean, theoretically speaking, you can implement this in a secure way to avoid cache attacks, to avoid timing attacks. But the first problem is that this is very tedious in practice. So there's a high chance of developers from accidentally still introducing either a cache attack or a timing leak. So I would not recommend that at all. The other problem is that a lot of times the Wi-Fi handshake is offloaded to the Wi-Fi chip itself, which is basically resource limited, and then always executing 40 iterations is just way too costly.
If you wouldn't recommend it, what solution would you recommend?
So that's the one. One thing I would recommend is to to allow the offline computation of basically the password element, so it doesn't have to be recomputed every time you perform the handshake. And the second one is mentioned here, to use a constant time way to do it. And there's a RFC being written with several ways to do that.
In other words, modify the protocol.
Unfortunately, yes.
I'm sorry, Christian, we don't have time for any more questions at this point. Perhaps you two could take it offline. Okay.
Yeah, I'm free to discuss things offline as well today.
All right. Thank you. Let's thank the speaker again. All right. Our next speaker is Joe Lee. He is a assistant professor at UC Irvine, and he's going to be talking about DNS interception. So let's give him a round of applause before he gets started.
Okay. Thank you for the nice introduction, and welcome to my talk. So my name is Joe Lee. I'm currently an assistant professor at UC Irvine, and this is a joint work with my co-authors from Tsinghua University, Fudan Universities in China, and UT Dallas. And actually, one of the co-authors, Haixin Duan, is sitting there. So if you guys later have questions regarding our talks, you can come to us during the break. So let's get it started. So the topic of this talk is about the DNS security, and let's first give some. Okay, so first let's give a quick background overview about DNS. So in this talk, we focus on the DNS resolution process. Essentially, say if you have a client, you want to get an IP address of a domain name, for example, IETF.org. So typically you will go to a recursive resolver, and then the recursive resolver will handle all those resolution process for you, like going to the different authoritative servers, like the root name server, top-level domain name server, and the second-level domain name server to get the IP address of your domain and then give back to the client. So when you have a contract with ISP, typically they will give you a default recursive resolver for you to use. But now it turns out more and more users prefer to use this public DNS resolver. We have Google, we have OpenDNS, we also have Cloudflare. They are very, very good. So I believe the major three reasons for the users to switch the public DNS resolvers could be the performance, could be the better security, and also the support for the DNS extensions turned out to be maybe better. So the security issues we investigate in this talk is that, say, as a users, you choose public DNS resolvers and you want these public DNS resolvers to handle your request. You still send that domain request to this resolver, but there are some unpassed middle boxes that can see your request and assume your DNS request is not encrypted. So what can really happen? And in particular, we look into this specific case, say, there's a guy on the path and basically intercept your DNS request and then redirect it to one alternative resolver and let this alternative resolver to handle the resolution. So then say the public DNS, Google will be kicked out completely from this picture, and this alternative resolver will do the query and the response handling and finally give the request to the user. So that's the main problem we look into in this work. And it turns out this kind of request tampering is really hard to detect because the alternative resolver can basically spoof the IP address. So it can pretend to be Google, and then if you are a client, you look into the source IP address of this packets, it's really hard to discern those cases. So we found that there are 4 types of potential interceptors doing this. Network provider, ISP is only one of them. Censorship, firewall also doing that. There have already been some reports talking about that, and antivirus software, malware doing that, and also enterprise proxies are doing that. As an example, for the ISP, we found there has been some reports and news about these practices, and actually this type of middle boxes is named as transparent DNS proxy by those parties. So it's kind of to be something known to the community, but in this work, we try to do a large scale, more comprehensive analysis instead of doing individual news reports. So that's the main contribution of this work. Okay, so basically the 2 main questions we want to answer in this research is, first, how prevalent is this approach, is this practice, how prevalent is DNS interception? And second, what are the characteristics of the DNS interceptions? What's their strategy, and what do they really like in practice? So let's first come to the threat model. So actually, in the previous example, we only introduced one way to do the DNS interception, and it turns out there are a few more ways to do that. So let's first come to our basic picture. Say we have those 5 parties. We have a client, public DNS, and then authoritative server. They are the normal parties handling your DNS requests and responses. And then now we have on-path device, and then one alternative resolver is likely to belong to the same owner of this on-path device. So when the on-path device doesn't do anything anomalous, anything suspicious, it should just forward your request to the public DNS and let the public DNS to handle everything. So the bad things happen when this on-path device try to change your request. So the first example we look into is this request redirection. So in that case, the on-path device will simply block your request to public DNS, for example, from Google, and then instead it will, redirect your request to its own alternative resolver, and then the alternative resolver will do the resolution and the response handling. Actually, there's another case for the DNS interception. So in that case, the on-path device will replicate the request to different places. So first, your request will still go to the public DNS and then get resolved. In the meantime, the on-path device will copy the same request and issue that to its own alternative resolvers. So from the perspective of authoritative server, there will be 2 requests, and then 2 responses will go to the client, and typically the first one go to the client will be cached and used by the client. And there's also a third category of DNS interception. So in that case, the request to public DNS is still blocked, and then the request will be sent to the authoritative resolver. But when this happens, the authoritative resolver stops from sending your request to the authoritative server, but instead it will directly give you the response to the client. So in the end, we are looking to those 3 types of issues during DNS interception. And next, let us take a look at the methodology. We try to detect those kind of DNS interception practices. So actually, from the previous 3 examples, you may already have some idea to detect this. Because say if you are able to control the clients and you're also able to control some authoritative name servers, and you're able to direct your client to send some requests to your own authoritative servers. And by looking into the differences between the request patterns from the public DNS resolvers and authoritative resolvers, you are able to discern those cases. The main reason is like if by looking into the source IP address of the request going to authoritative servers, if the source IP address does not really belong to, for example, Google, belongs to something you have no idea about, nothing relevant to Google, and then you can figure out there may be some issues with the DNS resolution process. So actually, this is what we do. We do this end-to-end data collection and comparison. We do control some clients and let them to send a large number of requests, and then we also control some authoritative servers and to receive those requests and then do some comparison. But still, there are 2 major challenges we need to address. First, how can we gather those large number of the vantage points? I mean, those middle boxes, some of them are very close to the clients. So if we want to observe enough of those DNS interceptions, we need a large number of vantage points. So we actually leverage 2 platforms. The first actually comes from Proxy Rack, which is SOX residential proxy networks. Actually, as a client, a customer, you can buy its services, and it's a peer-to-peer proxy network. So you can actually send your request to its gateway, and then the gateway will find a peer in its pool, and then let the peer to redirect your request to some places else. So we can actually leverage a large number of IP for us to do this measurement study. So in the end, this is the first one we use, but the limitation for that, it only supports TCP, and we will know DNS is major based on UDP. So to measure the UDP DNS request, what we do is to actually work with a company in China who we have a good relationship with, and allows us to write to put our code in its network debugger modules. So we actually implement our measurement logic and let it to run on the client devices. So by doing that, we're able to measure both TCP and UDP. And the second challenge we need to address is how we're able to see the policies of interceptions of the middle boxes, because they are kind of black box. We cannot really go there and then open the box and see how they implement their rules. So what we are trying to do in the end is to enumerate all the possible policies, and this is the best effort approach. So we actually focus on 5 types of fields. First is the public DNS resolvers that destined by the users to handle the request, and second, the different protocols, and third, different types of requests, and also we look into the different types of TLDs. And finally, there's a particular challenge here is how we're able to link the requests from the clients to the requests sent to the authoritative servers. Because when the request comes through all those middle boxes, the source IP address will be changed. So there's no obvious way to link that. So in the end, we develop this trick. Say we actually encode the unique ID for the source into the domain name, and it turns out those middle boxes don't really change the domain name. So by doing that, from the perspective of authoritative name servers, we can link the request from its original senders to the ones received by themselves. Okay, so in the end, by using these two platforms, we're able to send 6 million requests to the public DNS resolvers and to our authoritative name servers, and we have good coverage of the geolocation. So actually, we have more than 170 countries observed in our data set, and more than 3,000 autonomous systems AS in our data set. So we believe this is a really good data set to look into. So due to the time limit, I will only talk about 3 major observations during our study. So first question we want to answer is how many queries are intercepted. Actually, we look into the 2 different platforms. For the global-wide analysis, we have about 1,700 AS, and it turns out in the end, there are 198 AS doing interception. And for the experiments in China, we found from those 356 AS, there are 61 AS doing interception. So those numbers actually are not small. So we think this turns out to be an issue we really need to take good care of. And then we also look into the differences between the public DNS resolvers. And it turns out if you are trying to go to a more public, maybe more popular, like well-known public DNS resolvers, the chances your request get intercepted may be higher. So actually, if you are in China and then you use Google's public DNS, if you are using UDP, 28% of a chance your request will be intercepted. And if you're using TCP, the ratio is smaller. And actually, we have one recursive resolver set by ourselves, actually under China's EDU network. And turns out the ratio is much smaller. So actually, I think it makes sense because I don't think, those EDU DNS resolvers are known to them and they are interested to them. And the second question we want to answer is how are my queries intercepted? We talk about 3 types of DNS interceptions. The request redirection, request replication, and direct responding. It turns out in most cases, those middle boxes will do the request redirection. A small ratio will do the request replication, and then for the direct responding, it's really, really rare. And the third question we want to answer is, are my response tempered? I think for the security perspective, this is the most important question we want to know. And it turns out that actually the message is kind of positive, in some sense, because most of the responses are not tempered. From the 6 million responses, only hundreds of them are going to change without users' consent. And there's one interesting case we want to briefly go through here is traffic monetization. So actually, if you are in China and then you belong to this China mobile group of Yunnan autonomous system, if you use Google's public DNS and you send a request of Yahoo's IP address, and then your response will be changed to this app advertisements IP. So actually, this app advertisements also belong to the same AS. So they actually somehow monetize their traffic from your DNS requests. Okay, so I'll quickly go through some way we think about that can address this issue. So first, we think this issue should still be taken care of, even though it turns out the response tempering is not too much, because I think from users' perspective, it's their right to know who is really the person, the party handling their request. So far, there's no way for users to know that. And secondly, we found those open resolvers security is not really good. Actually, only 43% of them support DNSSEC. And we found for those resolvers using the banned DNS resolution toolkit, it turns out all of those versions should be deprecated well before 2009. So they are using all those very vulnerable versions that are really not good. So 2 tips about addressing this problem. First, we think DNSSEC is still a relevant technology to address this issue. Even though those recursive resolvers may ignore DNSSEC as a client, if you do verifying your response from using DNSSEC, there's a chance you can detect such response tempering and then prevents these bad things from being happening. And the second suggestion we want to give is to use encrypted DNS. For example, if you set up a TLS connection between you and recursive resolvers, and you can somehow use the certificate to verify, okay, this turns out to be the right recursive resolver, or this turns out to be something I have no idea about. So we know there are some very good, very interesting RFCs working on this direction, and we believe this is the right way to go to. And in the meantime, we also provide this online check-in tool. So even without encryption, if you go to our website, you can clearly see who is the real DNS recursive resolvers you are using. And to conclude, we did the first large-scale measurement, end-to-end measurement on this issue of DNS interception based on alternative resolving. And then we have some interesting findings. For example, we found there are 259 AS doing this. And if you are in China and you try to use Google's public DNS, should be really careful about that. And then there are some security concerns. And finally, we think there are some mitigations, and we also propose an online check-in tool. And in the end, we think this issue should be, addressed by the efforts of the community. So we have more details in our paper, which was published in Unique Security last year. And here are some my personal information. If you want to send questions for discussions with me and with other authors, feel free to do so. Thank you so much.
We have time again for one quick question. It's coming up to the mic. I'm sorry, only one. I'm sorry. No, you. Yep.
Okay, so again, Florin Baboscu, Broadcom. In your measurement, did you refer to mobile networks or fixed networks? If it is a case of mobile networks, did you consider a local offload, or did you consider internet PDN that it is solved through an operator network?
So actually, we have two platforms. For the second one, the one with the security software, that is a mobile network. So for the details of the network operators, I need to check the papers and also with the students, but I think we can discuss later. We have the details in the paper.
Yes, I'm asking you because at least in the context of the mobile network, the creation of the internet PDN, which I assume that it is the one on which you are operating, practically provides you with a DNS solver. And practically there, it's a functionality, it's not a threat.
Okay.
All right, let's thank our speaker again. All right, so the next talk will be on Oblivious DNS, given by Paul Schmidt, who is an associate research scholar at the Center for Information Technology Policy at Princeton University. So let's give him a round of applause to get started.
Thank you. Is this on?
Yeah.
Okay. So this is work where this was actually presented at PET's symposium last week in Stockholm. So in the interest of time, I've got matching slides as the previous talk, so I'm just going to sort of jump through this very quickly. What we're looking at with conventional DNS is you issue this query and you're sending it typically to your ISP, which is running a recursive resolver. And then it goes out to the rest of the DNS hierarchy in the world. And so the problem with that is that the recursive DNS resolver has all kinds of insight that they can use to see both your identity in the form of your IP address and basically all of your actions on the internet. So you can easily put together a database of users and what they're doing, like one user is going to Google and Amazon, another is going to Bing. They can also see what types of devices you have on your network. And so because of that, these recursive resolvers can be the targets for data requests. So an oppressive regime can simply say, hey, you need to hand over all of your DNS logs. And so it's this dangerous position where we're sort of trusting these ISPs or any recursive resolver to hold all of this information. There are these cloud services, Google, Quad9, Cloudflare, that are offering recursive resolvers openly, and they say, you know, obviously they're not going to keep logs, which is likely true. There's too much data to actually sort of store this kind of thing, but it doesn't actually solve the problem. they're promising to throw things away doesn't fix anything. We're still trusting them. We're just shifting trust from our ISPs to these resolvers. And so that, that's fundamentally, there's still a problem there. You may have heard of other DNS privacy-focused work, like DNS over TLS or HTTPS. That's just encrypting the transport, so that's going to fix things like eavesdroppers between you and the resolvers, but the resolver still gets to see all of your queries and your identity. QNAME minimization hides things from the rest of the DNS hierarchy, but it doesn't solve the fundamental problem here. And so what we've done is we've designed a system that we call oblivious DNS, which essentially separates the user identity from the queries at the recursive resolver. We built this with the requirements that we had to be compatible with existing infrastructure. It's very hard to change DNS software on authoritatives or at recursive servers. It's a really old ecosystem. It's just not simple to sort of throw things out and build a new protocol altogether. We also had to minimize overhead because DNS underpins basically all web traffic. So what we did was we made a couple changes. The first was we modified the stub. Stubs normally operate as lightweight processes on your OS. They take care of DNS resolution for the applications on your machine. And what we did was we use AES symmetric keys that we generate on the fly, and we encrypt your query to a ciphertext. We then append a domain that we own, something like, imagine we own the tld.odns. So we append this clear text domain, which means the recursive server is not going to be able to understand your query. It's just ciphertext, but it will use the existing DNS infrastructure to eventually reach our authoritative that we own, say .odns. At that point, we've got this ODNS authoritative server, which is both an authoritative server and a recursive server. It holds the public keys or the private key to decrypt the session key. Session key decrypts the query. It then acts as a recursive and does the entire process over again, going to root TLD and the actual genuine plain text authoritative. So this separates the client identity because that is held at the recursive server, the ISP recursive, and the ODNS authoritative gets to see the actual query, but it doesn't get to see the user because we're essentially tunneling DNS over DNS, and we're abusing the existing recursive resolvers out there. Of course, we're introducing these operations, and there's going to be some overhead. So what we did was we measured this. We implemented a stub and our ODNS resolver in Go, and these tests were done on the same machine, so there's no sort of WAN latency. And what we see is, as expected, the symmetric crypto is really lightweight. You can generate your keys, you can encrypt your domains, you can decrypt the domains very, very quickly. We used elliptic curve crypto for the public key. The reason being, in the larger paper, we explain, we cram all of this into the QNAME of DNS queries, and so there's this very limited space. And so if you use something like RSA, those keys are gigantic. That's going to be much larger than you can actually issue in a DNS query. And so we use this elliptic curve crypto, but overall we see about 1 to 2 milliseconds additional latency to every query for doing this. We use standard libraries. So if we use this, and this is on my laptop, so if we use a server class machine with optimized libraries, things should work a little better. We then fed the Alexa top 10K domains, and we see conventional DNS outperforms ODNS by about 1 to 2 milliseconds. Overall, though, we feel like we're not doing too poorly just with the standard libraries we're using. So that's one piece of the latency. The other thing that we introduced is WAN latency, because we're tunneling to this ODNS resolver. Essentially, that round trip time to that resolver is added to every query. And so you can see this illustrated in this figure. We've got conventional DNS. Our client was in New Jersey. And you can see Cloudflare is doing quite well. You've got Google and Quad9 are the other solid lines. And then we used ODNS resolvers. One was in New York City, which is about 4.5 milliseconds away from us. And the other was in Georgia, which is about 19 milliseconds away. And what happens is basically that RTT is just appended to all queries. So this obviously motivates some kind of, we need a widespread deployment of ODNS resolvers. You can't just have a single ODNS resolver out there in the world because you'd introduce a huge amount of latency for a large number of people. So we argue for a widespread Anycast deployment in order to sort of get nearby. Because we're using Anycast, this introduces a problem because we're using this public key crypto to decrypt the queries or decrypt the session keys. And we can't just hand out the same public key to all servers on Anycast. That would be incredibly unwise. And so what we do is we have a special request that is sent on that Anycast address. And at that point, the ODNS resolver that you're nearest, according to BGP, will respond with its name, which is, us1.odns, something like that. And it sends back its public key. At that point, your client can do this, once a day, once an hour, whatever, in order to find the nearest server and then use that domain specifically to append all queries in the future, and you'll know the correct public key to use. So that's all fine and good, but what happens when you actually use this on the internet? And web page load time is the metric we decided to look at. Here we use 30 top Alexa top 30 websites and loaded them using both conventional DNS, using the Princeton resolver, and the ODNS resolver that we had set up. You can see a few, the right-hand bars for each is ODNS. You can see for a few pages we're a decent amount slower. So Craigslist, Instagram, Facebook, those mostly things that had a lot of little objects are what we are a little bit slower on. But overall, we're performing pretty closely. There was one that was very odd, live.com. It turns out that's because we were directed to entirely different CDN. And in the ODNS case, we had a single giant JavaScript bundle. And the traditional resolver went to a CDN where there are lots and lots of little JavaScript objects to download. So that was a little bit slower. The other one that we were curious about is Reddit and New York Times. How could we possibly be faster than the conventional DNS in those cases? Because we are introducing this latency. And it turns out if you look at the time to first byte for those sites, it starts to make sense. Essentially, we were directed to CDNs that were closer. We just happened to be, our ODNS resolver directed us to a more optimal CDN for us rather than the Princeton resolver. So this really argues for, again, having this widespread Anycast network of ODNS resolvers because you need to be directed to objects that are near you. Of course, when we do this, when we're sending these ciphertext queries, we're essentially ruining the caches of existing recursive resolvers. And they're not going to like that, so we wanted to understand what this would look like in terms of traffic. So we took a trace of around 8 million queries and simulated users as we're turning up and down the percent of users that are using ODNS. And you can see when you have 0% of ODNS users, the cache misses at the recursive are relatively small. As you increase the percent, that's obviously growing. However, if you implement caching at the stub, which we do, we actually reduce the overall percentage of traffic. We're not inventing the wheel here. There are some stubs. I think Windows stub actually caches right now, but not every stub does. So just doing that actually helps quite a bit. Even if you're caching just a single user, you can get quite a benefit. So overall, we don't think we're introducing too much traffic. We also were worried about undesirable cache entries. So we set our responses with a TTL of 0, which should mean do not cache this. However, some resolvers out there ignore that value entirely. Some actually treat 0 as a special value where they permanently cache it. And so we had to measure this and try to understand it. We did the same set of simulations with where we were varying the percent of ODNS users, and then we varied the size of the cache at the recursive. And you can see if you have a very small cache, something like 1,000 entries, ODNS is going to be painful. We're introducing something like 15% of churn and entering these ciphertext queries into the cache, which is not ideal. But really, in reality, recursive resolvers have much larger caches than 1,000, and overall, we don't see it. It's not that bad. So just to quickly wrap up, there are other things in the full paper that we talk about. We deal with EDNS 0 client subnet, which exposes some of your IP address, your client identity to the ODNS resolver. We deal with queue name length with the very limited space, and then the encoding that is used. And then where do we go with this? We're thinking about policy-based routing, where maybe users might be interested in selecting ODNS resolvers based on sort of location or ISP, or maybe they can choose to say us.odns to avoid certain locations around the world. So with that, I'd be happy to take any questions.
All right, so any questions?
It seems there's a potential issue here in that deployment can be subverted. If I was an ISP that wanted to subvert deployment of this, to be clear, I'm not. I could implement my recursive resolver that I advertised to transparently forward ODNS queries, which then subverts the whole purpose of not putting the ODNS infrastructure in the position of having to be the third party that the user has transferred their trust to. Mm-hmm. I think there's maybe a way to address that in the design if you have space to do it, but you might not have space.
Yeah, that's a good question. There is the sort of issue that we essentially need to count on the fact that those two are separated, that the recursive and the ODNS resolvers are separate, which in practice is a difficult problem. Yeah, I'll have to think about that.
That there's at least one recursive layer that exists.
Exactly.
Even, and that's
exactly.
Separate. Yeah.
All right. If there are no other questions, let's thank the speaker one more time. Thank you. You tested it earlier, right? You tested it earlier, right? Try unplugging it back in. Please stand by. Technical difficulties. I don't have USB-C. I don't have a USB-C. A USB stick. No, I don't. No. But it would need to go on. You sure you tested it earlier? Excellent. All right, thank you. This is your adapter. Okay. Faulty adapter. No worries. All right. Yeah, I'll advance for you. Yep. All right. Sorry, everyone. Thank you for bearing with us. So the last presentation is on some costs of DNS, DNS over TLS, and DNS over HTTPS for the modern web, given by Austin. Please, let's give him a round of applause before he gets going.
All right. Thank you. You can go ahead and advance to the next slide. Yeah, so DNS privacy has become a significant concern. We know that on-path network observers can spy on and tamper with DNS traffic. This is the DNS that you all know and love, DO53. That's how I'll be referring to it for the rest of the talk. So 2 protocols have been proposed to encrypt DNS traffic. There's DNS over TLS, or DOT, as I'll refer to it for the rest of the talk, defined in RFC 7858. And then there's DNS over HTTPS, or DO, defined in RFC 8484. Let me advance the next slide. So the contributions of our work, we performed an extensive performance study of DO53, DOT, and DO, and we give some general insights to optimize DNS performance. So again, we really want to understand how DO53, DOT, and DO affect the end user experience. And there are a couple of metrics that we measure in order to give us that understanding. So first we measure query response times. We wanted to reproduce Mozilla's findings. So for those of you who don't know, Mozilla did a couple of studies where they measured DO query response times. They also measured effective ECS on user performance, things like that. We wanted to see if we could reproduce the results on DO query response times, measure page load times. Again, this is what we think are really important to users. They want to see if they can load New York Times and how DO might affect those page load times. And we also wanted to see if you change network conditions, things like additional latency or loss, how that affects your user experience. Okay, so this is kind of a general overview of our setup, very simplified, but the general idea is that we have a client, which is at Princeton University. We will perform traffic shaping, so an emulated 4G network, lossy 4G and 3G. Again, these are not actually connecting to mobile networks. These are just emulated conditions. You're performing queries to recursive resolvers at, again, Princeton's default resolver, Cloudflare, Google Quad 9, for each unique domain name that is embedded in a web page for images, links, things like that. And then you're actually, in steps 3 and 4, going to load content from these web pages that you just performed DNS queries for. And we use the Tranco top list, which I believe was presented at NESS. It's just taking basically Alexa, other top lists, averaging it over a period of time. So you can think of this as a list of just top websites that we want to measure. Again, things like New York Times, other stuff. So these are response times from Cloudflare's resolver on Princeton's network. You can see in the legend at the bottom in blue, we have all of Cloudflare's settings. So Cloudflare DOT, DO53, and DO. And then by default DO53, I'm referring to the university resolver at Princeton, which only supports traditional DO53. So if you could go ahead and hit next. You can see some interesting characteristics. One is that for about 50% of queries, you can see that Cloudflare's DO actually takes over Cloudflare DOT, and it's faster. And if you could hit next again, you can also see, it's kind of hard to see right there, but actually at the very tail of query response times, that Cloudflare DO not only overtakes its own DO53 implementation, but also the university's DO53 resolver, which we thought was very interesting to see. And you see similar characteristics with Google's resolver that, if you could hit next, please, that for about 20% of queries, again, DO seems to outperform DOT. And you can see a similar phenomenon as you saw with Cloudflare, that DO is once again outperforming DO53 for the very tail of query response times. And then lastly, this is Quad 9, right? So you can see at the bottom that this is Quad 9 DOT. if you could hit next, please, that for about 90% of queries that DOE is outperforming DOT. And then you can see similar behavior, once again, as with Cloudflare and Google, that for some reason, DOE is outperforming Quad 9's DOE 53 resolver. It does not outperform our university's DOE 53 resolver, but nonetheless, you see this kind of similar behavior that for some reason, DOE is outperforming DOE 53 for the tail of query response times. So again, the takeaway seems to be that for some reason, DOE is outperforming DOE 53 for some percentage of queries. There are multiple reasons we think this might be, one of which might be caching of the DNS wire format. So for example, if the recursive resolver already has the answer in its cache, and maybe the transaction ID is some fixed number, as it is implemented in Firefox's implementation of DOE, which I believe it's set to 0, maybe they're caching the wire format of the DNS response, which allows them to more quickly send a response back instead of having to construct a DNS response each time. And this result that DOE is outperforming DOE 53 in the tail of query response time seems to support Mozilla's findings. Next, we wanted to measure page load times, which again, we believe reflects the end user experience. And for this talk, we're only going to show page load times for Cloudflare, but if you look at our full paper, which we have the archive link for at the bottom, we also show page load times for Quad 9 and Google. So as mentioned before, we also wanted to see how changing network conditions affects the end user experience, how it affects query response times, page load times. So we performed some traffic shaping to emulate mobile networks. Again, want to state that these are not actually connecting to real mobile networks. We didn't tether a phone, but we wanted to see just, if we could emulate network conditions, how would these protocols perform across different recursors? So for 4G, to emulate that, we added 53.3 milliseconds of additional latency, millisecond of jitter, 0.5% loss. Lossy 4G, same amount of latency and jitter, but now we're doing 1.5% loss. And then lastly with 3G, 150 milliseconds additional latency, 8 milliseconds of jitter, and 2.5% loss. This is based on data that was provided in a report by OpenSignal. And again, we talk about why we chose these networks in the full paper. So these are page loads when you use Cloudflare's resolver from Princeton's network. So you can see the way you can read these graphs is that this is taking all the page loads that were performed using Cloudflare, for example, DOT on the left graph, minus the page loads that were performed using Cloudflare's DOE 53 implementation. The vertical line is the median, right? So this is the median difference between DOT and DOE 53 in terms of page load times. The white background indicates that this difference is between plus or minus 30 milliseconds, right? So the kind of key takeaway from this slide is that if you're using DOT or DOE, the difference in page load times on a university network to Cloudflare's recursor is only 30 milliseconds. You can go to the next slide. And the picture starts to change a little once you move to an emulated 4G network. You still see on the left plot that DOT is performing within plus or minus 30 milliseconds in page load times compared to DOE 53. But now if you look at DOE, this picture starts to change, right? So the background indicates that the median difference between DOE and DOE 53 is over 100 milliseconds, right? The actual median here is about 153 milliseconds. So again, once you go to a emulated 4G network, DOE starts to drop in performance, but DOT stays about the same. And again, the picture changes. So now the blue background indicates that DOT is performing actually better than DOE 53 when you're on a lossy 4G network, which is a pretty surprising result, right? And now DOE has actually moved back to being within plus or minus 30 milliseconds from DOE 53. So all these numbers are starting to change around, but the picture seems to be that across these three networks so far, again, the university network, the 4G network, and the lossy 4G network, DOT has remained either indistinguishable or slightly faster than DO53. And now, this is an emulated 3G network. So now both DOT and DO are over 100 milliseconds slower than DO53. So again, to remind you of the conditions for an emulated 3G network, we added 150 milliseconds of additional latency, 8 milliseconds of jitter, and 2.5% packet loss. So now the conditions have become so dire that both DO and DOT are significantly slower than DO53 in terms of page load times. So what does this mean, putting this all together? It seems to be that if you're running DNS over TCP as a transport, that this can actually help page load times. We saw that across the university network, the 4G network, lossy 4G, that DNS over TLS was performing either indistinguishably, and by that I mean plus or minus 30 milliseconds in terms of page load times, or it performed actually slightly faster than DO53. And we believe this is because TCP packets can be retransmitted as soon as 2 round trips. So as we're tweaking the loss, more and more DNS packets are getting dropped, and this means that they could be retransmitted faster than something that's being defined by a timeout, perhaps a couple of on the order of a couple of seconds for a traditional DNS over or traditional DNS timeout. So this helps it's okay. This helps DOT and DO perform well on lossy networks. Okay, so we think to conclude that there are several potential improvements for DO53, DOT, and DO. You could send what we believe are called opportunistic partial responses. So maybe you say to a recursor, here are all the different questions I want the answers for, and then the recursor, as they get authoritative answers, will send them back to the client, right? We also believe wire format caching could help, as previously discussed. So in Firefox's DO implementation, the transaction ID is 0 by default. And so what this means is that once an answer is cached on a recursor, it knows what the exact format of the response is going to be. So you could simply cache the entire wire format instead of having to read the answer from cache each time in terms of the DNS cache. This could instead be an HTTP cache. Lastly, we believe that HTTP2 push for DO could significantly help performance. So HTTP2 push has been talked about in the mailing list for DO for quite some time, but this is something that we believe once implemented widely could actually significantly help DO performance, because you could push answers to the client, or the web servers could push answers to the client for domain names that it already knows the answer for that are on the web page. So in conclusion, we seem to see that DOT performs better than DO on average, and even sometimes better than DO53. But nonetheless, DO has potential. Again, as I previously discussed, with potential improvements, with server push, DO could actually improve in performance quite significantly. The choice of your recursor and the network conditions matter, and we believe the transport characteristics of TCP should be further explored. Thank you, and you can check out our full preprint at the bottom with the archive link.
Let's thank him. All right, Lorenzo.
Lorenzo Calidi, I'm curious about if you tried multiple UDP retry strategies, because that sort of would really heavily influence the results. I know that the Android resolver has like a 5-second UDP retry timeout, right, which is basically you're going to like lose any race with DOT or DOH.
Right. We did not try multiple strategies, but we think that's definitely something that would fit into future.
It is documented which one you did use in the paper?
So like we just used Debian as our default client. So I think the default timeout with that was in resolve.conf, I think 5 seconds, as you said.
Okay, thanks.
Mm-hmm.
Hi, Puneet from Google Public DNS. So thank you for doing this research. It's good to see all the detailed information here. The one thing, as you mentioned in the beginning, and I'll point out again, is you've only done this from the Princeton University campus in Northeast US, right?
Correct.
So it's a heavily connected, well-connected part of the world. So the results here are not going to be representative for people who are in places where the connectivity is not as good.
Right.
So that's one important point. So I think the fact that you'll share the data, that will help us get more information from other sources. One of the things which I think keeps coming up here, I want to point out is part of the reason DOE works better is because it has an async API, while the DOT and DNS over 53 don't have that. And I'm curious if anyone has an async API for the traditional DNS transport, so we can compare that. Right. So if actually you could include that, that would be great. Then we'll tease apart the transport differences versus the API differences.
Yeah, that's something we've actually talked about in our next work of trying out different asynchronous APIs to kind of tease that out. So as you said, that's definitely something we want to look into.
Just to make sure you heard that, that's Get DNS API is the asynchronous API for the traditional DNS transports.
Okay, thank you.
Eric Nygren, Akamai, also on the perspective of only doing that from the from a Princeton vantage point, I think from a what is the impact on the page load time performance is really not going to be at all representative of the impact on CDN mapping, because going to a like a non-ECS Cloudflare resolver from Princeton versus going and using the local Princeton resolver is probably going to get you to the same place for CDNs, just given how it's connected, which is going to be. Whereas if you're in some part of the world where there's a local on-net CDN cache that may only be accessible via users within that local network, you're not that may have a performance impact on page load time you're just not going to observe in this case.
Thank you.
Giovanni and CDN. Clarifying question. You told before that all the queries you made were like random or unique queries. Is that what you did in your measurements?
What do you mean random?
How you handle? My question is there any caching involved in this process? Or?
No, we're starting with a clean cache each time. So our measurement is on a Docker image, and each time we start it up, we're getting a fresh DNS cache.
So which query names are you sending?
So these are all, each time we're making a page load, we read. So I guess this is something I should have mentioned in the talk, but we actually have a separate client, which for DNS queries, we're using dig for DNS over port 53. For dot, we're using stubby, and for DOE, we're using curl. And the reason why we did that is we noticed some peculiarities in the DNS response times in the HARs that we collected to get page load times. This is something we discussed more in the full paper, but we're starting with a fresh cache each time and using, again, dig, curl, and stubby in order to make these queries. We're pulling out the domain names that we saw in the page loads and making those queries separately.
Yeah, because, all right, that makes sense. If you talk to a resolver operator, you're going to see that they have a very high cache hit rate. So maybe it would be nice to extend your work to cover also cases where there's cache hit. It'd be also interesting.
Thank you.
Yeah, I guess you partially answered my question already by saying that you use curl, but do you include the connection time in your TCP, like when there is TCP DNS over TLS and HTTPS?
No, that's not in our data.
Mm-hmm. All right.
Thank you.
All right, let's thank the speaker one last time, as well as all the speakers in this particular session. Now we're going to take a break for lunch, which is in the next room over, and we will see you all when we return at 12:15, at 1:15.
Thanks for working with me.
No, it's fine. That was.